I recently started working on chapter 2 of the book Problem Solving Strategies by Arthur Engel, which is about colouring problems. That means problems where you find a colouring that proves that something's impossible. And the thing that's impossible so far has been being able to tile some shape with copies of another shape. Or tile a sort of grid of squares, or a grid with some squares removed, or things like that. And you find the technique is to find a colouring of the squares of the thing that you're trying to cover, and then to argue something about how the shapes, what you can say about what colours the shapes cover, and get a sort of impossibility result that way. I found them quite a lot easier than the invariance problems, although in a way some of them are actually invariance problems of a special kind. But that may be just because it was the first 6 exercises on the sheet, so let's see how things go. If I carry on, so I got up to question 6. So the next one is question 7. So what does that one say? It says, is there a way, the answer's bound to be no, because that's the point of these questions, to pack 250 1 by 1 by 4 bricks into a 10 by 10 box. And we note that 1,000 divided by 4 is indeed 250, so it's not a daft thing to ask to do, but so now we want to colour the points in sort of 1 up to 10 cubed in such a way that so this feels like a bit like one of the questions I've done already. So I'm wondering whether an addition mod 4 colouring is going to work here, because that's just I'm going to suggest. So what I'm hoping is that if I colour with a addition mod 4, I'm not going to have the same number of boxes of each colour, but each of these things is trivially going to cover one of each colour. So I'm going to try colouring the point x, y, z by x plus y plus z mod 4. And so then if I take a 1 by 1 by 4, that's just going to be taking one of these numbers and taking 4 consecutive values of it and keeping the other 2 constant. So I get 4 consecutive values of the sum, and so I'll use all 4 colours exactly once. So it just remains to check that the number of, because 10 is not a multiple of 4, I'm fairly sure that the number of things of each colour is not going to be the same for the 4 colours. But how do we prove that in an efficient way? That's going to be slightly tedious, or is it? Maybe I sort. Perhaps it'll probably be slightly easier if I think of 10 by 10 as 0 up to 9. So I've got 0 up to 9 cubed. So now I'm hoping that the number of ways of making 0 as the sum of 3 things is going to be more than 250. Is there a way of seeing that without being super unpleasant? I think I might try and do something that I did rather like that with one of the other colourings. So what I'll say is that I can certainly colour.
Yeah. I'm just doing the floor, so don't come out for 10 minutes.
Okay. I can cover 0 up to 7 cubed, the number of colours in 0 up to 7 cubed of each colour, number of points of each colour is going to be the same. And then what about, in fact, I can get up from 0 up to 7 cubed, but I could have also just done 0 up to 7 times anything. So I could have 0 up to 7 times 0 up to 9 squared, and then 8, 9 times 0 up to 7 times 0 up to 9. And so what I'm saying is I can, this set here, because of this 0 up to 7, will have the same number of each colour. This set here will have the same number of each colour because of this 0 up to 7. And then this set here, 8, 9 cross 8, 9 cross 0 up to 7 will have the same of each colour. So I'm only left with 8, 9 cubed, and that should be fine. So I'll have, which is equivalent to 0, 1 cubed. So how many, what are the possible sums? 0, 1, 2 or 3, and I'll get that 1, 3, 3, 1 times, so not the same number of times. So that was a slightly nicer way of proving that the colouring didn't colour everything the same number of times. But the basic idea of finding the colouring, that was sort of, again, fairly easy, just the first guess worked. An A by B, so this chapter seems to like just stating things and not putting them as questions, but just, you obviously have to prove the thing that's stated. An A by B rectangle can be covered by 1 by n rectangles if and only if n divides A or n divides B. If looks all right. If n divides A or n divides B, then obviously we can just, if n divides A, for example, I'll just draw that. If n divides A, then we can just do a rather obvious covering. It's really annoying that colour and cover are very closely close to being the same word. I've made that mistake many times already. So the only if part, it looks to me as though addition mod n is going to be again a very good candidate for the answer. So if I add mod n, so in other words I colour xy by x plus y mod n, it should be the case that I will not get the same number of each colour. And again, is there a quick way of showing that? I think there probably is, by roughly the same technique. So I'll go up to the largest multiple of n that is smaller than A, and the largest multiple of n that's smaller than B. And then I can, so that's a multiple of n, so I can cover this thing evenly. And in fact, even that as well, that's a multiple of n, so I can cover that much evenly. So I'm just left with this little rectangle where both things are smaller than n, and I want to argue that the number of times that we cover, so the number of times that the colors occur is not the same for every color. And so I've got some R and some S, and I know that R and S are both less than n. So the number of ways of making naught mod n, it's a little bit complicated. So the number of ways of making naught mod n is, I'll think of this as naught up to r minus 1 and naught up to s minus 1. So it actually depends a little bit on whether r and s are smaller than, you know, if they're sort of on how big they are. So if r and s are both smaller than n over 2, for example, then I'll be in good shape, because I won't be able to make n minus, well, I won't be able to make n in very many ways. But so what I sort of know this, but we're convolving two intervals. So what we get is a function that looks like this. So the number of ways of making naught. Just let's think of these as naught up to r minus 1 and naught up to s minus 1. To start with, I'm not going to reduce mod n. So I'm going to convolve the characteristic functions of these two. So what I actually mean is, how many ways are there making naught? There's one way of making naught. How many ways of making 1? There are 2 ways of making 1. How many ways of making 2? There are 3 ways of making 2, and so on, until we get to, let's say r, without loss of generality, is less than or equal to s. So how many ways are there of making r minus 1? We can make it r minus 1 plus 0 all the way down to 0 plus r minus 1. So there are ways of making r. And then if r is actually less than s, then we get r ways of doing things until we reach a certain point, and then it goes back down again to 1, and that 1 is counting the number of ways of making r plus s minus 2. And when we reduce mod n, we're going to take a chunk of this sequence and add it to an earlier chunk. And the only way that we're going to be able to get a constant function if we do that is if r minus 1 down to 1 lines up with 1 up to r minus 1. And so for that we would need, so this was the number of ways of making no, an easier way of thinking about it is that this r minus 1 is the number of ways of getting r minus 2, and so we would need that to be the set, we would need r minus 2 congruent to r plus s minus 2 mod n, and that's just not going to happen because s is less than n. So if you didn't follow that, it's just, that was my personal way of checking that we don't get the same number of each thing mod n. I don't see a really nice way of doing it, but that probably is a slick way of doing that. But finding the colouring was turned out to be an easy job for that question. One corner is the next question, so it's number 9. Of a 2n minus 1 by 2n minus 1 chessboard is cut off for which n, oh, it's one of these ones, so for which n can you cover the remaining squares by 2 by 1 dominoes, so that half the dominoes are horizontal. Okay. First of all, I just want to just check it was 2n minus 1 by 2n minus 1. Ah, it wasn't. It was 2n plus 1 by 2n plus 1. So now we get, that's 4n squared plus 4n squares to cover. So 2n squared plus 2n dominoes. Just a sort of sanity check there. And therefore we're asking for which n can we have n squared plus n vertical dominoes and n squared plus n horizontal dominoes. It suggests that, just the wording of the question suggests that you can always cover with dominoes somehow. I think I might just quickly check that, and it might be a little gentle easing into the problem before I think about colorings. So I can see that it's very easy to cover this with 1, 2, 3, 4, but if I were to insist that half of them were horizontal and half were vertical, it doesn't look quite so easy. In fact, I don't think I can do it when n equals 1, and I bet I can do it when n is 2. I'm guessing it's going to depend on the parity of n. Not with 100% confidence, because there could be something slightly subtler. Right, let's just try and do this one. Yeah, this one's going to be possible because I can just first of all do that, and then I can just, I've got 4 2 by 2 squares, and so I can just do 2 of them horizontally and 2 of them vertically. There's lots of ways I could have chosen to do that. So, and this construction here works when n is even. So when n is even, we can cover the remaining squares by 2 by 1 dominoes and get half of them to be horizontal. So I'm guessing that when n is odd you can't, so let's try and find a colouring that will demonstrate that. It's obviously not going to be just a straight black and white colouring, because every domino will cover exactly 1 black and 1 white. So what property do I need the colouring to have? One of those, there seem to be 2 ways these things go. Usually, either you find a colouring such that the dominoes are balanced in some sense with respect to that colouring, but the thing that you're trying to cover is not balanced, or it's the other way around, that the dominoes are somehow not balanced enough, but the thing you're trying to cover is balanced. And how many, if n is odd, n squared plus n is still going to be even, so that doesn't really help. Or does it? If n is even, n squared plus n is also even. So I guess it's a bit more complicated than parity, but I haven't quite decided whether I want the whole thing to be unbalanced or the whole thing to be balanced. And in what sense? Well, the fact that we divided this up into little squares suggests that an old friend might be useful here, which is the colouring that goes 1, 2, 3, 4. It just takes a 4. So I don't have a very good reason for doing this. But what was my reason? I did have some reason. And it was, yes, it was just that because this colouring is taking a 2 by 2 thing and just sort of translating it about the place, and because the covering that I found here also involved partitioning into 2 by 2s, it seems as though there could be some relationship here. So I'm going to see whether I can prove, just using this, the case n equals 7. Not n equals 7, actually. I mean 2n plus 1 equals 7, so n equals 3. So that goes up to 1, and then 3, 4, 3, 1, 2, 1, 3, 4, 3. I better go down here. 3, 4, 3, 4, 3, 4, 3. How many have I got? 1, 2, 3, 4, 5. So 1, 2, 1, 2, 1, and then up here 1, 2, 1, 2, 1, 2, and then I won't put anything there at all. Okay, so when I start using dominoes, each horizontal one is going to cover. Now, why would this do anything at all? So what we can't do with it, oh no, that doesn't help. So that we've got 48 squares to cover, so 24 dominoes, so 12 of each colour. Sorry, 12 horizontal and 12 vertical. Can I say something about the number of... So what I can certainly say about a horizontal one is that it either covers a 4 and a 3, or it covers a 2 and a 1. So let's look at the sort of the number of 4s plus the number of 3s minus, I could even maybe go for plus. No, I don't want to do that. Now minus the number of 2s minus the number of 1s changes by 2 if horizontal. What can we say about the verticals? We get the number of 4s plus the number of 2s minus the number of 3s minus the number of 1s changes by 2 if horizontal, if vertical. And so at the end of it all, if we're covering with, I'm just quickly wanting to look at, when we've done all this, we get 1, 2, 3, 4, 5, 6 extra 1s. So let's just look at how many of each colour we've got. So we have 3, 4, 8, 12, 15 1s, by symmetry 15 3s, 3, 6, 9, 12 2s, and 12 4s. No, not 12 4s. Something's gone wrong here. My symmetry was wrong. It's 12 3s. The symmetry is between 3 and 2. Just check that adds up though. 15, 27, 39, 48. So can we make 15, 12, 12, 9 if at each stage we're allowed to add or subtract? So we out of so if I put a horizontal one down, then I've got no ones, no twos, a 3 and a 4, or a 1 and a 2, no 3s, no 4s. So 12 of those, and 12 of these. And I think the answer is going to be no. But why? I seem to want an invariant, I think. So I want something that vanishes on all of these vectors, which is going to be something like 1, minus 1, minus 1, 1. Let's just check that. If I take the inner product of this with 1, minus 1, minus 1, 1, that's 0. And then if I take it with this, it's 0. If I take it with this, it's 0. If it's this, it's 0. I kind of knew that a little bit off by heart by thinking about, having thought about, well, it was a simple thing to guess because of things I've thought about to do with Hadamard matrices and things like that. Is the inner product of this with this 0? We get 15 plus 9, which is 24. Oops, take away 24. That's embarrassing. So that invariant, so to speak, which felt rather promising, didn't actually work. But the fact that I needed 12 of them, oh yes, so that just shows that I can make 15, 12, 12, 9 out of these things. But, sorry, it doesn't show that, but it shows that I may well be able to make them. But it doesn't show that I can necessarily do it if I have to use exactly 12 of each kind. Now, how would that help me? Well, I could do it in a sort of slightly unpleasant way, which is I can say I have, when I use 12 of these, I'm going to get A, 12 minus A, 12 minus A for some A, and for this I'm going to get B, 12 minus B, B, 12 minus B. And then I've got some simultaneous equations, but I've got rather a lot of equations. So A plus B is 15. 24 minus A plus B is 9, which I know anyway, so those two equations are dependent on each other. Oh dear. So let's just do this. A plus B equals 15. And then A plus 12 minus B equals 12. So A equals B. So it's a parity thing. Which is impossible because A and B can't be 7.5. So I have actually proved it for 7, but by an ugly method, which clearly is going to generalize, I think. But I would rather yes, I would rather. Well, maybe I think I'm going to just see what that proof does in the general case, and then try and make it slightly less ugly. So the number of in general, if I've got in general, I go 1 2 1 2 up to 1, just up to 1, and then no, that's wrong. That's a 3. 1 3 all the way up to 1 3 4. This is 2n plus 1. So the number of ones is n plus 1 squared minus 1 ones. Because I've got n plus 1 ones along here, n plus 1 ones along here, and then this one is removed at the last minute. The number of twos is n times n plus 1, n plus 1 threes, and the number of fours will be n squared, I think. Fours, because it's sort of n and n. Does that look as though the numbers agree with when n is 3? It does. 16 minus 1, so 3 times 4, 3 times 4, 3 times 3. And so I've now got, I can make I have then the number of horizontal dominoes n squared plus n, either 0 0 1 1 or 1 1 0 0. That's saying that all the horizontal dominoes will either give me no 1s, no 2s, a 3 and a 4, or a 1 and a 2, no 3, no 4. And then I've n squared plus n of 1 0 1 0 or 0 1 0 1. And so now let's look at the first couple of equations. So I get n squared plus so I haven't completely finished. So out of that I make n squared plus n minus n squared plus n minus a, and out of the other one I can make b n squared plus n minus b n squared plus n minus b. So we then get that a plus b needs to equal n plus 1 squared minus 1, and a plus n squared plus n minus b has to equal n plus 1, and so a equals b equals n plus 1 squared minus 1 over 2, so n must be even, because that has to be odd, so that when I subtract 1 I get an even number. I feel there's a nicer way of saying that. It seems that I only really needed to look at the number of ones and the number of twos. So can I see that in a sort of slicker way? So each horizontal thing covers the same number of ones and twos, and each vertical one covers a different number of ones and twos. And the difference between a number of ones and a number of twos is the difference between these two. And I rather suspect that parity argument is going to make that work. Actually, I think I'm not going to explore that because it won't be all that nice, much nicer than what I've just done. It'll be just a different way of phrasing it. And I'd rather just do one more question before stopping, unless it's so easy that I feel I have to do yet another one after that. Figure 2.3, okay, shows 5 heavy boxes. I can quickly draw figure 2.3. It's got T's in each one for some reason. Which can be displaced only by rolling them about one of their edges. This looks... so yes, I'm assuming these are 3D boxes perhaps. They're tops, yep. Are labelled by T. Figure 4 shows the same 5 boxes rolled into a new position. So let me just draw that. And here it goes like this. Like this. Which box? That's brilliant. Not at all the question I was expecting. I was expecting sort of, can you get to this position? But actually, which box in this row was originally at the center of the cross? Okay, well, this is not going to be totally easy. So if I can do this, I think that'll be I'll stop there. So I have a huge clue. I would never have thought of trying to find a coloring if I'd just seen this problem in isolation. But let's just... So I think I want to think first about what you can do with a single box by rolling it around. So where can it end up and how can it end up? Facing in a different direction, and so can you, for example, with a single box, can you just rotate it by 1 by 90 degrees or something? I suspect you can't, but that might be worth thinking about. So don't see how to do this without drawing a fairly serious picture. So if I rotate about this edge here, I get to, so this was the original square it was sitting on. So I now get a new cube, and that T has gone sort of backwards to there. If I now rotate it sideways, so those are the 2 squares where it used to be. What's happened to that T? It has now become like this. And then if I rotate it back in this direction, I end up with a T that looks like that, that's just next to the square where it started. So I can rotate by 90 degrees, but only at the cost of also translating. Now I'm beginning to think that maybe something happens like a vertex. Yeah, if I just think where the vertices go, It looks to me as though they are always going to be of the same color if I color the vertices of the grid black, white. So so supposing I just color the vertices of a cube in an alternating way in the obvious sense. So if those are lined up so that they go on the grid with a black going onto a black and a white going onto a black and so on, when I rotate it, it'll still be aligned with the right coloring. So that certainly puts a restriction on what can be done. And so let's just think about this. So let's suppose that the top vertices are, let's make this one black, white, black, white. Which means that the bottom vertices will be just like this, except I'll have the opposite colours. So the one that's just underneath this will be black and so on and so forth. Does that help us much? I'm going to guess that this is my guess, that one has to have been the middle here because it could have, it's part of this row of 3, but then I need to ask myself. Actually, first thing I want to do is see whether I can reach this configuration and how I can do it. That won't prove that it had to be done in only one particular way, but it'll be perhaps a useful step in that direction. So I know that I can rotate that by 1 and get it to here. And if I do that, can I rotate it in the other direction? So that's another useful thing to ask. So I went up and then I went to the left and then I went down. But supposing I'd gone down and to the left and up, I'm guessing that I will have rotated it through the other way. So let's just check that. So if or do I need to check that? Or can I argue some abstract way that must be what happens? I think I'll just check it the boring way. So first step will be to go, it'll have a pointing down thing, but over here. The second step, that will be having me pointing to the right. And so that when I go back up, it'll point to the right. Yeah, so the sort of doing this, but instead of going up, left, down, if instead I go down, left, up, it'll be ending up pointing the other way. So that means that I can and the fact that these things are in the way, I think, doesn't matter too much. So I can always move this. If I sort of come right away from it, and I can move it so it's facing horizontally, or yes, I call that vertical, and I'll call it vertical if it's upside down as well. So I can move it so it's horizontal, vertical, horizontal, vertical, horizontal. And I can't move this so that it's next door, but still vertical, because if it's still vertical and next door, then the colours won't match up properly. I'll have a black thing going to a white place, which never happens. That I think is the proof really. So the only one that can go to here, which moment? Okay, so this moves an odd number of places, 1, 2, 3. This moves an even number of places, 1, 2, 3, 4. So we can make this arrangement. I haven't quite demonstrated how to do it, but I more or less have. So it's clear that this guess of an answer is the correct answer. But a quick proof that that this must work. So the center here is the one that has an odd distance from all the other ones. So we want something that's got an odd distance from all the vertical ones and an even distance from all the horizontal ones. And the only one that has that property is this one here. It's got an odd distance from here, odd distance from here, even distance from here, odd distance from here. Whereas that one, for example, has an even distance from another of the vertical ones, and that's sort of hopeless. And this one's got an odd distance from one that's of a different orientation. So I think that has proved it. Maybe could have done that a little bit more quickly. So just to summarize what the proof actually is, this coloring of the vertices shows that if you've got a rotated cube, so again, I call a T like that vertical and a T like that horizontal. So if you move a cube and then end up with a T on the top again, if you move it an odd distance, you have to change whether it's horizontal or vertical. And if you move it an even distance, you mustn't change whether it's horizontal or vertical. And so since these all start with T's that are vertical, then whenever you, so that just says that whichever one corresponds to this one here will have to have an odd distance from everything that's of the same orientation, and an even distance from everything that's of the opposite orientation, so to speak. And that's the only one that does the job. That is a very nice question, I think. Because it really is just a little bit surprising that just a colouring has something to do with it. And that's a nice place to stop. And so it looks as though I'll get through these reasonably quickly, but they are getting a bit harder now. I've started to have to think, so that's nice too.